Hey all, welcome to homeschool. Hope you guys are very much busy preparing for your examination. To give maximum benefit for your examination, I have started application question series on all the chapters where I have already covered two chapters, that is acids, bases and salts and management of natural resources, and this is my third chapter I selected, that is the human eye and the colorful world. So today, let us see the previous year question papers, most asked questions, okay, most repeated questions. If you look at the previous 5 to 6 years question papers of all the boards, I'm talking about CBSE as well as SSLC board. So let us discuss about this repeated questions. Coming to the first question is there on a board. What is spectrum of white light? How can we recombine the components of white light after prism has separated them? So first, here there are actually two questions. One is, what is spectrum of white light? So what do you mean by spectrum of white light? It is nothing but splitting of white light into its component colors when you pass through a prism. Yes or no? Whenever you pass white light through a prism, white lights get splitted up into its component colors. So that a band of colors is what we call spectrum, isn't it? So what is the definition you can write here? Splitting of white light into its component colors. Its component colors is called spectrum. Okay, so if you take a prism, so whenever you pass a white light, obliquely, so what happens? This particular white light will split up into 7 colors, isn't it? So this band of colors is what we call it as spectrum. Okay, so this is our first question. And coming to the second part of a question, how can we recombine the components of white light after prism has separated them? So once you separate the components of color into 7 colors, once you get a spectrum, so how can you combine them again to make a white light? Say just by placing an inverted prism, isn't it? So when you place an inverted prism near it, say all these splitted colors, when they are coming out through this inverted prism and they combine, and you will get it as white light. And you will get it as white light, isn't it? So let me show you a single thick line here. So this is your white light. Right? So what is the answer you will write here for the second question? By placing a prism inverted to the prism which has splitted white light. Yes or no? So you have to place one more prism in an inverted position to this prism, so that whatever splitted light is there, when it passed through this prism, and ultimately all of them would combine once again and they would come out through this prism as white light. Okay, so this is what the answer for this question. Clear, everybody? So spectrum is what, and how do you recombine the splitted colors once again into white light? So it's very simple, by placing a prism inverted to this particular prism, right? Okay. And coming to the second question, and this question is definitely it is based on atmospheric refraction. Atmospheric refraction, isn't it? Say, read the question carefully. Explain why do stars twinkle but planets do not. See, this is a very, very famous question, and this has been asked repeatedly in the question papers. okay, in one or the other way. So definitely I can give you 3 stars for this particular question. Very, very, very important. So question is, why do stars twinkle? So first try to understand what is that twinkling of stars. See, whenever you look at the stars, it appeared brighter sometime, and again soon after that it appears slightly dim, again brighter, dim, bright, dim. That's how the stars appear. Yes or no? So this is what we call twinkling effect. So why do stars twinkle like this? It is because of atmospheric refraction. So what is the answer here, guys? Atmospheric. Stars twinkle. Stars twinkle due to atmospheric refraction. So now the big question is, what do you mean by this atmospheric refraction? See, our earth is covered by atmosphere, isn't it? Say, imagine this is our earth. Okay, so our earth is surrounded by atmosphere, right? And stars are somewhere here in the sky. Yes, space, they are in the space. Fine. And imagine the starlight, I mean the radiation emitted by a star, light emitted by a star is called starlight, right? So when the starlight is coming from a star, imagine you are there on earth. Okay, this is a person there on earth. So starlight has to reach this person, and it should go through the so-called atmosphere. So between you and star, there is something called atmosphere, isn't it? And what does the atmosphere contain here? Atmosphere contains so many gases. It contains not only gases, so many components it has. It has so many, gases, solids, dust particles, and various other things are there. And even the temperature conditions of atmosphere also keeps changes. Sometimes atmosphere is very much hot, sometimes it is cold. In some areas it is hot, in some areas it is cold, So temperature of atmosphere is not always a constant thing, right? And it keeps on changes. And also you have so many gases in the atmosphere. So all of them will refract the light in a different way, because each and every gas nature is different. Each and every gas has its own refractive index value, right? So the way they refract the light is also different, right? So what happens here? Starlight, okay, the moment it reaches from vacuum to atmosphere, a certain level of refraction it undergoes. Okay, it undergoes a certain level of refraction, isn't it? Say, bending of light took place in the atmosphere. Not only one set of refraction. Say, imagine this is another layer of atmosphere. So it undergoes refraction like this. Again, it undergoes refraction, something like this, right? Say the refracted ray, when you project it back, so here is your star appearing for you. Exact position of star is here. Because of this continuous refractions, multiple refractions, I call it as multiple refraction, because one set of refraction occurred here, right? Another level of refraction occurred here. So it is because there are various gases present. It is because the temperature conditions are different in the atmosphere from one level to another level. So various levels of refraction is occurring, and finally the refracted ray is what reaching your eye, right? So when you project back that refracted ray, that is where you can see the star. Exact position of star is here, but you are observing your star in this position. Okay, you are not observing it in exact position. You are observing somewhere here. This is what we call apparent position of a star. Clear? And now the amount of starlight reaching to your eye is also continuously changing. I repeat once again, amount of starlight reaching your eye is continuously changing because of this so many levels of refraction. Okay, so because of this, your star appears brighter sometimes, dimmer sometimes, brighter sometimes, dim sometimes. Okay, so this is what we call twinkling effect of star. Clear, everybody? So what are the points that we can write for this question is, say first point is stars twinkle due to atmospheric refraction. Now you have to elaborate what is that atmospheric refraction. Okay, so since atmosphere is made up of different components. That means you will have so many gases in the atmosphere, different components. Starlight undergoes, starlight reaching your eye, reaching our eye, undergoes multiple refractions. Okay, and starlight continuously changes. Okay, it appears brighter sometime, and dim sometimes. Okay, so this causes stars twinkle. Okay, so this is what we call twinkling effect of star. Now one more question is there, why do planets do not twinkle? Okay, so the reason is, say I'm writing answer for the second question, why do planets do not twinkle? Planets do not twinkle because they are bigger in size. They are bigger in size. Okay, and they are near to Earth. Compared to stars, the planets are near to Earth. And planet is nothing but a collection of so many small point sources. Okay, so understand carefully, planet are the collection of many point light sources. So here twinkling effect of one point is nullified with another. So twinkling effect of one point is nullified by another point. So planets do not twinkle. So what do you understand by this? See, very simple, guys. Planet is very bigger than the star, and what I'm telling you is planet is a collection of so many light sources. Like in a planet you will have, imagine so many small stars. Planet is a collection of so many small stars. Each star I am calling it as one light source. I mean that gives a starlight, yes or no, that can reach our eye. So that's why I am calling planet is a collection of many small stars or small points. Say imagine this, in this particular thing, this particular star or the point is brighter, right? And at the same time another star would become dim, right? And at the same time the other star would become brighter, the another star would become dimmer. Say here one star is becoming brighter, then immediately at the same time the another point is becoming dim. It's like continuously every time one or the other star, one or the other point would remain brighter. Though the remaining ones have become dim, continuously one or the other point would become brighter continuously. right? So you would observe that planet being a brighter one. Okay, say you will not observe the planet becoming dimmer. You will always observe the planet being brightest. It's because it's a collection of so many small points, where some points would be brighter, some points would be dimmer. Again, the dimmer points would become brighter in the next time, in the next point, right? So that keeps the planet always look brighter for us. Clear? So here the twinkling effect of one point is nullified by another. Nullified in the sense it is cancelling. Twinkling effect of one point getting cancelled by another. Because the moment this guy has become dim, no, the other guy would become bright, isn't it? So that's the reason we call the twinkling effect is cancelled by one another. So because it is larger in size, it is the collection of so many point sources. So that's the reason planets do not twinkle but stars twinkle, right? So this is a very famous question. So the question can be asked individually. They would ask you only like, why do planets do not twinkle? And they would ask you, why do stars twinkle? You know, so this is what the answer you have to give for this question, right? So now we will go for the next question. Coming to the third question. Name the atmospheric phenomenon due to which the sun can be seen above the horizon about 2 minutes before actual sunrise. So why does the sun appears 2 minutes early? We can see the sun 2 minutes early before a sunrise, right? So that is actually due to, again the answer is atmospheric refraction. Atmospheric refraction, right? Due to the different conditions of atmosphere, you know, the light that is coming from the stars or the light that is coming from the sun continuously undergoes refraction. We call it as the light undergoes multiple refraction, isn't it? So here also the answer is atmospheric refraction. Okay, so since the question has come, I am explaining the concept in a detailed way. Actually, 2 points you need to remember here. Due to the atmospheric refraction, first thing is we see the sun 2 minutes before the sunrise, okay, and we see the sun 2 minutes after the sunset. That means our day is actually 4 minutes longer, isn't it? Because of this, I can say day is 4 minutes longer. Yes or no? The question can be asked this way also. Why is the day is 4 minutes longer? It is because we see the sun 2 minutes before the sunrise and we see the sun 2 minutes after the sunset also. So what may be the reason for this? Yes, I told you atmospheric refraction, right? Okay, let me explain this particular concept in a diagrammatic way. So imagine, first you need to understand what do you mean by the word horizon. So horizon is a point where the earth and sky get separated. See, horizon is a point where, what did I tell you? The earth and sky is getting separated. Where you can observe this, when you go for the beaches, when you stand on a shore and observe far away to the beach, you would observe a point where the earth and sky has been separated, right? So that is what we call horizon. So we see the sun whenever sun is coming out of the horizon, right? Imagine this is your earth. This is your earth, right? And you know, somewhere here, this is your horizon. This is your horizon. So sun is here. You will see the sun whenever sun comes above the horizon. If you want to see the sun from your eyes, sun must come above this horizon. So horizon is a point where earth and sky is separated. Earth and sky is separated. This is the sky. This is the earth. So this point where earth and sky is separated is called horizon. So sun is below the horizon now. You will only see the sun when the sun comes above the horizon. Okay, so imagine before a sunrise, what happens is, see, sunrise you will observe when the sun is coming above the horizon, isn't it? Okay, see, now you observe around this earth you have something called atmosphere, right? So as I have already told you, atmosphere is made up of so many components. The temperature conditions of atmosphere is different, so that whichever the light passes through the atmosphere, it undergoes multiple refraction, I told, isn't it? Okay, so now imagine the light from a sun is reaching the atmosphere. Okay, it is reaching the atmosphere and it would undergo, multiple refraction. Yes or no? This is the atmosphere, bending of sunlight takes place. So now this is how the refraction occurred. And now if you project this refracted light, here you would see your sun, right? Sunrise did not occur, but still somewhere the sun is here below the horizon, very much below the horizon, right? So this particular light, the moment it reaches the atmosphere, it would undergo the refraction. So the refracted ray is what you would observe, right, with your eyes. So the refracted rays, if you project, see, it is appearing that sun has already crossed the horizon. In fact, to be frank, in reality, sun is still there below the horizon. But because of this atmospheric refraction, it is appearing, it is seeming that sun has already crossed horizon and it came above. That's how you will see the sun 2 minutes before the sunrise. Okay, so similarly, during sunset also, sun would have gone down below the horizon, but still because of this atmospheric refraction, for about 2 minutes you would see the sun being above the horizon, so you can see the sun even after the sunset. Okay, sun has already set, sun has gone below the horizon. Because of this atmospheric refraction, it appears as the sun is there above the horizon, so you can see the sun, right? So because of this early sunrise and late sunset, our day is 4 minutes longer. Clear? So this is what the entire concept of the question. So for this question, the answer is just 1 mark. It's a 1 mark question. Answer is just atmospheric refraction, because I am just telling you the various ways of asking a question. Okay, so they would ask you, why do we see the sun 2 minutes before the sunrise? Or they would ask you, why do we see the sun 2 minutes after the sunset? Or they would ask you, why is our day is 4 minutes longer? So for this, I gave you the explanation. Clear, everybody? So these are the questions relating to a concept called atmospheric refraction. Okay, and now we will go to the questions relating to scattering of light. Look at these questions, guys. So these questions are on a concept called scattering of light. So now we will learn what is that scattering of light and what are the reasons for these questions. Clear? See, along with the questions, I am covering the concept also here. So try to understand carefully. See the question, what is the color of the sky during daytime? Give reason. So we all know what is the color of the sky? It is blue. Yes or no? So what is the reason for sky being blue in color? It is because of the scattering of light by atmospheric particles. Okay, so here what I can say is our atmosphere has many gases and other particles. Yes or no? We have other particles also, like dust particles, smoke particles, so many particles are there. And these particles and these gases their size is smaller than wavelength of white light. Smaller than wavelength of white light. And again, we all know white light is made up of 7 colors. Each color has its own wavelength. Yes or no? So these gases and other particles size is smaller than the wavelength of those radiations, those colored radiations. Okay. So when these radiations reaches the atmosphere, these particles will scatter the radiation. Okay, and usually the gases and other particles which are present in the atmosphere will scatter the blue light stronger compared to the other lights, other radiations, other colored radiations. Okay, so blue color is scattered all over the atmosphere because these particles are scattering in the sense spreading. So these particles are spreading the blue radiation faster compared to other colored radiation. That is the reason the sky is appearing blue in color. Okay, so what I can write here, when sunlight reaches atmosphere, these particles scatter blue radiation stronger than others. Okay, so blue light is scattered all over, and that reaches our eye. So sky appears blue in color. Okay, so this is the answer for that. So whatever the light has scattered in the atmosphere, spread in the atmosphere, who had spread this blue light? The gases and various other particles present in the atmosphere have spread this blue light all over. So whatever the light that has spread, that will reach our eye. So the sky appears blue in color. Clear? So it is due to scattering of atmospheric particles. Okay, fine. And usually we all know in the 7 colors Βᴇ, right? Violet, indigo, blue, green, yellow, orange and red. These radiations have smaller wavelength and these radiations have longer wavelength. Usually the radiation which has smaller wavelength is scattered more compared to the longer wavelength radiation. Okay, say usually violet, indigo, blue colors will spread more in the sky compared to the red, orange and yellow, because these guys, the red will not get scattered more, is because it is having a longer wavelength. Okay, so initially these radiations will reach the atmosphere faster, so the particles would scatter these radiations strongly, more nicely compared to the other radiation. That's why the sky is appearing blue color, because all these particles are spreading or scattering blue radiation more compared to the other radiation. Clear? Fine. And now you see the next question. The sky appears dark instead of blue to an astronaut. State reason. So where are these astronauts stay? They'll stay in a space, isn't it? Out of the Earth atmosphere, right? And when there is no atmosphere, how can the particles or gases can scatter the sunlight? When there is no scattering, the sky would appear dark only. It will not appear in a particular color, isn't it? So what is the answer here? Astronauts stay in a space. Where in a space you don't have any atmosphere, because in space there is no atmosphere. So no scattering of light takes place. No scattering of light takes place. Okay, so that's the reason the sky appears dark for the astronaut who stays in a space. Clear? So this is all about the scattering of light. And we'll see one more question here. based on the scattering of light itself. Again, these are very much famous questions on scattering of light. Question you can observe here: why does sun appear reddish early in the morning? Say sun appears reddish early in the morning and late in the evenings also. During sunrise and during sunset, our sun appears reddish in color. So what is the reason behind it? It is also like the same scattering concept. Say early in the morning, imagine this is our earth, isn't it? And this is the horizon. Horizon is the line that separates earth from sky. Say sun, this is the sun. Okay, so this is our sun, and you see the distance between the sun and earth. It is quite far. Early in the morning, the sun stays near the horizon or just above the horizon, right? So the distance is quite far, so the sunlight must travel a long distance. Sunlight must travel a long distance to reach our eye. Imagine this is human beings that are staying on earth. If you have to see a sunlight, sun is somewhere very far, just near the horizon, so its light should travel a long distance. We all know the sunlight is made up of 7 different colors, right? ᴄＧᴇᴄ colors. And now we all know violet, indigo, blue, green, yellow, orange, red. And these guys have, smaller lambda, smaller wavelength, and red light wavelength is longer, isn't it? Say what happens as this violet radiation, indigo, blue, green radiation, when they reach and they get scattered away. The moment they will try to reach near the atmosphere, again you have so many layers, right? So when these blue radiation, green radiation, all of them, when they reach, this is our atmosphere, you think. Okay, so when they reach the atmosphere, they get scattered immediately because their wavelength is smaller. Remember guys, the radiations whose wavelength is smaller will get scattered very, very early. Okay, and now the red radiation's wavelength is longer. So this particular radiation is least scattered. This is least scattered, and it can travel through a long distances. So this is what happens. These guys' radiations are very much smaller. The moment they reach the atmosphere, somewhere there only they get scattered. But red radiation's wavelength is very much longer, so it can travel. All other radiations would have scattered, only the red radiation is not scattered, so it can reach very nicely to our eye. So the red radiation is reaching our eye compared to the other radiations. That is why the sun is appearing red in color early in the morning and late in the evenings. Okay, because early in the morning and late in the evening, the sun's distance is very far from the earth. The sun is staying somewhere near the horizon. So, the sunlight or the radiation which is having longer wavelength is least scattered, so it can travel through a longer distance. So red radiation is what reaching our eye, so the sun looks reddish early in the morning and late in the evening, right? So this is what our concept. So what we can write the sentences for this question is, I would write the sentences somewhere here. Note down the points. Early in the morning, sun is near the horizon, and sunlight should travel long distance to reach our eye. Okay, among all the radiations, red radiation has more wavelength, lambda in the sense wavelength, so it is least scattered least scattered, so it can travel long distance to reach our eye. Okay, so this is the sentence that you can write for this question. Clear? Fine. Next question relating to this itself. Why is red color selected for danger signal lights? You must have seen the signal lights where the red means stop. Red color radiation you can see very nicely, isn't it, compared to the other colored radiations. So can you tell me why? That's the reason red is selected for danger signals. Okay, because the red radiation you can see nicely. Your eye can see red radiation very nicely compared to the other colored radiations. The reason is this only. Since red color radiation has less lambda, this is the answer for this question also. From here you can write. Red radiation has more lambda, so it is least scattered. It can travel long distances to reach our eye. Okay, so even if red radiation is somewhere very farer, you can see that red radiation from your eye very nicely, is because the red radiation travels longer distances. It has more wavelength, so it will scatter very less in the atmosphere. Okay, so that is the answer for this question. Clear? So with this, I have covered all the important questions on a concept atmospheric refraction as well as scattering of light. Clear? So with this, I am completing this particular video. Let us meet up with the next chapter, that is control and coordination. We will discuss all the important questions on control and coordination chapter. Do subscribe our channel to learn the concepts in the easiest way and in a detailed way. We have covered all the chapters of class 10 science and mathematics, where the links are provided in the description. You just can go to a particular link and enjoy the concept. Do like our videos, share and subscribe our channel. Thank you so much.